My name is Emmanuel Chan, and I study cosmology in the astrophysics department under the supervision of Professor Spergel. As a cosmologist, my goal is to understand the composition and the evolution of the universe. And in order to look back in time, astronomers look out into space. However, only the luminous matter, such as the one inside stars, is visible. Are we missing much? This is like looking at the Earth at night. What you see is not the people, just the cities. And by looking only at the cities, you miss 40% of the world's population. Well, for astronomers, things are way worse. The matter that we think of as normal, the one inside you and me and stars, only makes up 5% of the universe's content. So, how do we see the remaining 95%? There is a way to look at non-luminous mass, called gravitational lensing. Here's how it works. Mass grips spacetime, telling it how to curve. Spacetime grips mass, telling it how to move. In fact, light itself is deflected by massive objects. So by looking at the deflection of light, astronomers infer the presence of mass. You can try this for yourself. A massive object and the foot of a wine glass distort the light in a very similar way. When looking through this gravitational lens, the red galaxy appears stretched, or even multiply imaged. Although the glass is transparent, you know it is there because of the distortions in the image. Similarly, by looking at these stretched or multiple images, astronomers can reconstruct the mass that causes the distortion, whether this mass is luminous or dark. In fact, this is one of the most promising ways to learn about the dark components of our universe. And Princeton is a lead actor in the Hyper-Supreme Cam experiment, which aims at measuring this effect. In order to do this, astronomers need to measure the shape of galaxies. While this may seem very easy, in practice it can be very difficult, as we are often looking at very faint and blurry images of distant galaxies. And this is where I come in. My thesis work consists in matching the distortions in galaxy images with the distortions in the diffuse microwave background. Indeed, the light from the diffuse microwave background is also distorted by the presence of mass, in the same way as galaxy images are. Princeton plays a major role in observing this diffuse microwave background through the Atacama Cosmology Telescope, and identifying distortions in this background does not require measuring shapes. This is why I am developing new tools to combine the two in order to take full advantage of gravitational lensing surveys and eventually shed new light on the dark components of our universe. Thank you.